So today we're going to continue some more kinematics review. And remember, just like last day, the entire purpose of today's review is to prepare, of course, for our final exam. So in other words, this is coming from a perspective of end of year review. Anyway, let's get going. So today we are going to continue reviewing kinematics. We're not going to focus on the same things that we covered in the last video, but we are going to have just one little bit of overlap with some projectile motion review. So in other words, where we look at motion of objects that are moving not only in the X direction, but also the Y direction. And the nice thing about reviewing projectile motion today is it's going to tie in well with the other two things we're going to review. That's vector addition and relative motion. This is where you have things that are, it's kind of like projectile motion, except things that are moving in like a diagonal direction. So for instance, like, oh, something's moving north of west, for example. That's what vector addition was all about. We'll get there when we get there. Again, I recommend that you try some of the questions that I posed today before I go over them. But again, if you want to sit back and just watch, that's fine too. Here we go. So for a projectile motion question, we got Billy Bob Bo Bibbly. He's jumping his car over a 3.00 meter tall hill at an angle of 30 degrees over a mud hole. The car was in the air for a total of 3.44 seconds. What was the initial velocity of the vehicle? Highly suggest you pause the video here and give this one a try. All right, I'm going to go over this one now. This is a projectile question because it's going over a 30-degree angled hill. So what I would highly suggest we do, first of all, is just draw like a side picture of this. We know that it's coming off the top of the hill, and we know it's leaving at an angle of 30 degrees. So if we do like a dotted line representing our horizontal, 30 degrees might be something like this. The reason that's important is you can break that down into an X velocity and an initial Y velocity. And then, of course, that vehicle will come down to the actual ground, or I guess the mud hole in this case. So the car was in the air for a total of 3.44 seconds. So we have time. In other words, that's the thing that connects our X and our Y. So if we make a bank, that was a pretty miserable X. There we go. If we make a bank, X comps and then Y comps, we can start looking at how these things are related. First of all, time, we have T equals 3.44 seconds. That's on both of them because time is the one thing that connects both X and Y. We know the cliff is 3 meters tall. I'm going to say that's our distance in our Y direction. So that's our dy. I'll call that negative 3.00. The reason I'm calling it negative is I want up to be a positive direction. If the car is dropping to the bottom of a 3 meter tall hill, of course, that's going down. So I need to make it negative. We also know, since we have a Y direction, we know gravity is coming in here. So we have acceleration in a Y direction. That's going to be negative 9.81 meters per second squared up. What else do we have here? I guess we can look back at our X direction. We're looking for the initial velocity of the vehicle. That would be this true V on the angle right here. We know this is 30 degrees. If we have either our initial Y velocity or our X velocity, we can use some trigonometry to find our true velocity. I think really looking at, our X and our Y's, we don't really have a lot for X, but we have quite a bit for Y. I think it would be safe for me to find VIY and then use VIY in my triangle over here to find V using a little bit of trigonometry. So if I have a look at my kinematics equations, the kinematics equation that I'm going to use that has all these things in it is the one that says D equals VIT plus 1/2 AT squared. Let's throw our numbers in here. We know we have negative 3 equals VIY times T, which is 3.44 plus 1/2 negative 9.81 times 3.44 squared. Real exciting stuff here, I know. I'm going to clean up this part of this equation first, the whole 1/2 bit. So 1/2 times negative 9.81 times 3.44 squared. Everything else will stay the same. We have negative 3 equals, I'll pull the 3.44 out in front. So 3.44 VIY plus negative 58.043808. Okay, so we want to get VIY by itself. So I think I'm going to move this negative 58 blah, blah, blah over to the other side. So I'll just have to add that over. So I'm going to go negative 3 plus 58.043808. This is going to give me 55.43808. That's interesting. Hold on, I'm just double checking. Oh, I missed something here. 04. See, there we go. I knew something was kind of wrong there. 55.043808. 0.4308. Holy smokes, what's going on with my tongue today? Here we go. 3.44 VIY is what that's left over as. Divide by 3.44 on both sides. This is going to give us VIY equals 16.1157 and a bunch of other stuff, but I think I'll leave that there. So that's our initial velocity in our Y direction. We want our true initial velocity of the vehicle. So looking at our diagram that I drew in the top right-hand corner, that can help us. Notice that VIY, which we just found, that would be our opposite side. The true velocity would be our hypotenuse. Opposite and hypotenuse, if you come out of SOHCAHTOA, let me write that out again, SOHCAHTOA, opposite and hypotenuse is going to be sine. So I'm going to go sine of 30 equals opposite, which is 16.1157 over hypotenuse, which is V. We want to solve for V, so let's multiply by V and then divide by sine 30. So if I take that and divide by sine 30, make sure you're in degree mode, of course. I have V equals, and I guess now we can use our sig digs. We'll have only two sig digs because of this 30 degrees here. V equals 32 meters per second. And just for good measure, because velocity is a vector, it needs to have a direction. We can say that that's at an angle of 30 degrees. And I suppose that would be 30 degrees up. So there we are. 32 meters per second at an angle of 30 degrees up. Kind of cool, I guess, right? So projectile motion questions. Moral of the story is make X components and Y components. Time is what connects the two. Sometimes you have to draw a picture with an angle and stuff and then use SOHCAHTOA. There's a bunch of stuff that goes into these ones, right? So just takes practice. We have a lot of questions like this, I think, provided in the review booklet. At least I'm pretty certain. Maybe I shouldn't eat my words like that. Anyway, let's move on to the new things that we're going to cover today. So something else we covered way back in kinematics was vector addition. So I want you to recall that with vectors, which have both like a direction as well as a magnitude, with vectors, it is absolutely critical to break it down into X and Y components. When vectors are all added together, we generally place them tip to tail. So in other words, if we have several different vectors, we place the tip of one of the vectors to the tail of another vector, right? So we're just kind of drawing them all linked together. Now, the whole point of finding your X and your Y components is, let's say in this first vector, we have X1 and Y1. And then in the second vector, we have our X2 and our Y2. What I want you to notice is we could have actually like just jumped through this whole, motion here in one go by saying if we added our X1 and X2 together, we would have had like this really big, we can call it like XT for X total. And then same if we took our Y1 and our Y2 and added them together, we would have like a really big, Y total, I guess we could call that. And then from that X total and Y total, we could use like a little bit of Pythagoras to figure out our true final displacement using not only this angle down here, but also the magnitude of how far that went. Basically, the long story short is break things down to X and Y components, add them together, be mindful of direction, of course, like if Y suddenly went down, you have to count that as a negative. But find all your X and Y components, add them together, make one gigantic triangle, and then solve for that hypotenuse. And of course, keep your angle because that'll tell you your actual direction that you're dealing with. Now, before we get into that, I want to kind of like talk about breaking down vectors. So I'm going to start with a relatively simple question here. Let's suppose Shelby drove 12.5 kilometers at an angle of 20 degrees north of west. How far north did she drive and how far west did she drive? Maybe you want to try this one on your own. Pause the video here. I'll go over it in 1 second. Okay, so to go over this, really would help to have a picture. This right here, this direction, 20 degrees north of west, that bothers people sometimes. What I've always found what I have always found works is realizing that north of west is a little bit backwards. You should start by drawing the second direction. So start by going west and then draw north. Because think of it this way. You're going 20 degrees north of west. So if you go west and then go 20 degrees north of that, that's 20 degrees north of west. Long story short, I'll start by drawing a line to the west. So if this is our starting point, this way, that would be west. And then we're going to go 20 degrees north of that. So just a little bit north. We'd say that's about 20 degrees north of west. And her distance there was 12.5 kilometers. Now the question is asking how far north did she drive and how far west did she drive? It's really just asking us to break this down into X and Y components. The north component would be her Y, right? It's up and down. So if we look at y, we can see that's the opposite side of this triangle, and this over here that we were given is our hypotenuse. Opposite and hypotenuse from SOHCAHTOA. Let me write that out one more time. SOHCAHTOA. Opposite and hypotenuse, that would be sine, right? So we'd have sine of 20 equals y, that's our opposite, over our hypotenuse, which is 12.5. Multiplied by 12.5 on both sides. Let's see what we get. 12.5 times sine 20, and it looks like we want just 2 sig digs because of that 20 degrees. That's going to be y equals 4.3 kilometers north. And just in case you're wondering, I didn't have to change that to meters because we're staying consistent here. It's not like we're using a kinematics equation. We're remaining consistent, so I could leave that in kilometers. Next one, how far west did she drive? Well, it's just asking like what's the x direction, right? Now x in this case, that would be the adjacent side of this triangle. So we have adjacent and we have hypotenuse. That would be cosine. Cosine is adjacent over hypotenuse. So cosine 20 equals x over 12.5. Once again, multiply by 12.5 on both sides. Hold on, 12.5 times cosine 20. Once again, to 2 sig digs, I'm getting about 12 kilometers, and that's to the west. Really, it's like 11.7, but of course, the sig digs kind of throws us here. So yeah, 12 kilometers west. Hopefully that's pretty clear. Obviously, the questions that we're going to do are going to be a little beefier than this for the most part, like this next one right here. So for this question, a football player ran 15.0 meters at an angle of 50 degrees north of east, dodged another player, and then ran 35.0 meters at 10 degrees south of east. Find their final displacement. You might want to give this one a try. Give yourself lots of room on a piece of paper. Draw a good picture. I'm going to go over it in a second. All right, so here's where the good picture comes in play. I'm probably going to screw this up because it's really hard to do this on the tablet. I know that's my excuse for everything. But 15 meters, 50 degrees north of east. Remember my tip, draw east first. So if I'm saying he's starting here, I hope that's going to give myself enough room. I'm going to go east. Probably is far enough. And then 50 degrees north of that, that's actually quite a bit north. So quite a bit north of that. Oftentimes, by the way, you draw this with a dotted line. On second thought, that's exactly what I'm going to do, just so I don't mess up my picture even more. Draw a dotted line. There we go. We'll say that's about 50 degrees north of east, and we'll say that's our 15 meters. 15 meters, 50 degrees north of east, there you go. So then they dodge a player right there, and then they ran 35 meters, so more than twice this distance, at 10 degrees south of east. So once again, I'm going to draw east first. I'm going to go quite a far ways with this because he's going pretty far here. That's probably good enough. And then 10 degrees south of it, that's not super far south. Say that's about there. And then I'm going to draw a line all the way over here. And that'll be our 35 meters. And this angle right here is 10 degrees south of east. What we're trying to find is their final displacement. So in other words, from the starting point, we'll even just say start right over here, to our end point right over here, we want to find what that final displacement is. Now, I always have to admit, when I draw these pictures, right now it looks like his final displacement is a little bit to the north. Like he went east, and then he went some amount north, apparently according to my diagram. But I always kind of like take this with a grain of salt because it's entirely possible that I might have not drawn this correctly, and that he actually ended up a little bit to the south rather than a little bit to the north. Calculations, of course, will confirm this one way or another. Fingers crossed that I drew this right. It's not the end of the world if you don't draw your picture right. What really matters is that you're getting your calculations correct. So what I'm trying to spit out here is we need to break this down into all of our x and y components. This part of this first triangle, I'm going to call that x1. This one's going to be our y1. On our second triangle, this would be x2. And then on down here, this would be our y2. A lot of calculation you got to do here. These are really annoying, but just break it down, find all your x and y components. I'm going to start with x1. Notice that's the adjacent side of this triangle, and we have the hypotenuse. Adjacent on hypotenuse, just in case you need it written again, SOHCAHTOA. Adjacent and hypotenuse is going to be cosine. So this will be cosine 50 equals x1 over 15. Multiply by 15 on both sides, so 15 times cosine 50. I'm not going to round my sig digs yet because I need these numbers, but I need to round within reason, so I'll keep like 4 decimal places. I've got 9.6418. That's my x1. Now let's find y1. Y is going to be our opposite side here, so we're going to use sine. So sine 50 equals y1 over 15, multiplied by 15 on both sides. And we get y1 equals 11.4907, we'll say. Now, I just realized I forgot to do something. Really important to include directions on these things, and units, of course. So both of those are meters. In terms of x1, that is going to the east. In terms of y1, that is going north. Now, next thing we'll find, I'm just going to draw a dividing line here. We need to find our x2 and our y2. Notice x2 in this case, once again, that's going to be our adjacent side. And we have our hypotenuse, except this time it's 35 meters, right? So adjacent and hypotenuse, that's going to be cosine again. So it's cosine 10 degrees equals adjacent, which is x2, over hypotenuse, which is 35, multiplied by 35 on both sides. This gives us x2 equals 34.4683 meters to the east. And then we have to find y2. y2 is going to be our opposite side here, so we'll use cosine or sine. So sine 10 equals y2 over 35, multiplied by 35 on both sides, so 35 times sine 10. This gives me y2 equals 6.0777 meters, and this time that's to the south. Notice y1 was to the north, y2 is to the south, so we just have to counteract each other. Good news is I can tell by looking at this, I was correct with my diagram that this person did ending up a little bit to the north. But let's confirm this. Let's find our totals. Just for fun, I'm going to change pen color here. I'll change to blue. This blue is going to represent our totals. So I'm going to find, do a dotted line here. I'm going to go over some of my work, but that's okay. This dotted line that I just drew is going to be my total X. This dotted line up here is going to be my total Y. What I'd ultimately like to find, ooh, that was miserable. Let me try that again. What I'd ultimately like to find is this final line right here, which is our true displacement. That's our true final displacement. And I'll also need the angle that it's at as well. To find my total X, let's just divide this again. To find my total X, it's literally just going to be X1 plus X2. So we'd have just 9.6418 plus 34.4683. Throw that in my calculator. Give me a second. 9.6418 plus 34.4683. That gives me 44.1101 meters to the east. Awesome, right? Y total this time around. We got to be careful because one of these is north and one of these is south. Since the north one is bigger, I'll call that our positive. So I'm going to say it's 11.4907. And then the other one, since it's to the south, I'm going to subtract it instead. So minus 6.0777. This is going to give us, give me a second, 11.4907 minus 6.0777. This gives me 5.413 meters to the north, because that was my positive direction before. Okay, so long story short, we now know what that triangle is. In case you really need me to, I'll draw it again, just kind of smaller over here. So that is 44.1101. That's to the east. And then to the north, we have 5.413. What we're ultimately trying to find is this amount right here. I don't know if I really have a name for it. I'll just call it question mark, but we also need our angle that this is at as well. Notice this forms a right triangle. This is just right triangle trigonometry now, so we can use Pythagoras to find this. So to use Pythagoras to find our question mark, we're literally just going to say 5.413 squared plus 44.1101 squared equals that question mark squared. Hopefully you guys know how to do Pythagoras at this point, so I'm not going to show all my work here just because I'm running out of room. But I am going to calculate this real quick. Don't forget to square root your answer. So I got my question mark equals, and I care about sig digs now. It looks like only 2 sig digs because of these angles. That's kind of unfortunate. Oh, this is a really silly answer because it kind of kills our 44.1101. To just 2 sig digs, it's just going to be 44 meters, unfortunately. In reality, it's 44.4, but for 44 meters, that'll work just fine, I guess. Now we still need our angle. So our angle can come out of another kind of trigonometry here. I'll use the numbers that we had in the first place. So this is our opposite, and this is our adjacent. Opposite and adjacent means we can use tan to find that angle. So tan of that mystery angle right there is 5.413 over 44.1101. To solve for this angle, we just have to use inverse tan on both sides. So take the inverse tan of this fraction right here. Inverse tan of this side just gets rid of it. Long story short, the inverse tan of 5.413 divided by 44.1101. This gives me, to 2 sig digs, this one actually rounds up quite nice. This gives me 7.0 degrees. So long story short, just to get my answer all well and good, the final displacement is 44 meters at an angle of 7.0 degrees, and that would be north of east, because they went east and then north, so north of east. Whew. So as you may have remembered just by seeing this, these kind of vector addition questions are kind of a nightmare. They take a long time. There's a lot of calculations that happen. And unfortunately, with a lot of calculations, there's a lot of places that things can go wrong. The good news is when you have a written response question like this, as long as I'm seeing the work, you can get most of your marks correct on this one, right? I'm looking more for the process. Break it down into your X and Y components and add them together, right? A small mistake here or there, while it does kind of kill your answer, it's not the end of the world. Matter of fact, I wouldn't even be surprised if I ended up making a mistake in this question somewhere and that this is somehow not right. But fingers crossed, I think I did all my work correctly. Certainly looks pretty good to me. It also sounds pretty realistic. Anyway, we got a few more things we got to cover. This next one is relative motion. This is basically just where you have like two things that are moving relative to each other. So I want you to start by imagining two scenarios. In one scenario, there's a boat that's crossing a river that doesn't have a current, so it's just going to go straight across that river. And then the other scenario, there is a current, so the water's flowing in that river. Now, in both scenarios, the boat will feel as though it is following a straight line across the river. If you're chugging along, going across the river, regardless of whether there's a current or not, you're going to feel like you're crossing the river in a straight line. However, in the situation with the current, the boat will have been dragged downstream. Now, the impression that the boat is going in a straight line in each scenario is known as relative motion. It's the motion measured with respect to an observer. So to someone who's in the boat, if you were not looking at the shoreline, if you didn't have any other reference point, you'd feel like you're just going straight across the river. Anyway, I have this old picture here that kind of shows how this works. Not a huge surprise, right? The motion of a river boat with a current versus without a current, you can see clearly that there's some different paths that get taken. But as far as the people in the boat are concerned, they're going straight across the river. If it weren't for the fact there's a bush or whatever on the other side of the river that they're looking at, they might not have even known that anything weird was happening at all. But no guarantees, you know, it is what it is. Anyway, moving on. Let's do an actual question with this one. I think this is the second last question. Yes, it is. There's 2 more questions here, guys. We're almost done. So I want us to suppose an airplane is flying at 550 kilometers per hour north. There's a wind from the west blowing at 40.0 kilometers an hour east. Find the velocity of the airplane relative to the ground. You can pause the video here and give this one a try. So I'll go over this one now. Because there's a wind here, the airplane is not actually going to be flying directly north. The wind is going to push the airplane a little bit off, off its path. This is no different than when you're driving on a windy day, like driving a car, of course, on a windy day, and you can feel the wind pushing your vehicle. Of course, when you're driving, you're making adjustments, making sure that you stay in your lane and all that. But still, right, you're being pushed around by another force, right? So to do this, I think it's easiest to start by drawing a picture. The airplane is flying directly north. That's the way it's pointed, right? So I'll draw a line going straight north, and that's 550 kilometers per hour. Now there's a wind from the west blowing it towards the east. Maybe I should draw that 550 kilometers an hour on the other side now that I think about it, 550 kilometers per hour. The wind's blowing from the west, so it's blowing to the east at 40 kilometers an hour. So we'll say that's 40 right there, kilometers per hour. So the true velocity of the airplane relative to the ground, even though the airplane is pointed north, it's actually going to be following this path right here. So that is what we were trying to find here. This is kind of like the end of that last question we just did. You're going to have to use Pythagoras to figure out this missing value here, but then you're also going to have to use a little bit of trigonometry, like SOHCAHTOA stuff, to find the angle, because it does ask for a velocity, which needs not only a magnitude, but also a direction. So starting with Pythagoras here, this is going to be 40 squared plus 550 squared equals that question mark squared. Go real quick through this. 40 squared plus 550 squared. Don't forget to square root that answer. This is going to give me my question mark equals, we want 3 sig digs, 551 kilometers per hour. Kind of interesting. It's like the wind's giving it a little bit of a boost. It's going up by 1 kilometer per hour. You're going a little faster because of this wind. Now, of course, like I said before, because we need a velocity, we need to also know the direction it's going at. So we need this angle. We have already the opposite side and the adjacent side. I wouldn't use the side we just calculated because we did round that answer. So since we have opposite and adjacent from SOHCAHTOA, that tells us we're going to use tan. So tan theta equals opposite, which is 40, over adjacent, which is 550. Use inverse tan on that, just like before. And we have the angle to 3 sigdigs is 4.16 degrees. Now here's where you got to be careful. Notice it's going north and then it's going east. So this would be 4.16 degrees east of north, because we went north first, so it's backwards, east of north. Anyway, throw all this all together just so we have it as a nice answer. V equals 551 kilometers per hour, 4.16 degrees east of north. Really important that we get that east of north in the right order, right? North of east is not the same thing. This went north and then it went east. If you drew this a different way, you might have a north of east thing. I think the answer there would be, it's just a reverse of it. It'd be 85.8, I think, something like that. Whatever you do, it is what it is, right? Anyway, one last question. Believe me, honest, I swear, this is the last one we got today. So an airplane is approaching Calgary directly from the east. It is cruising at an air velocity of 700 kilometers per hour. So that's what its engines are thrusting at. A strong wind from the south is blowing at 90 kilometers per hour north. Find the direction the plane should travel in, or the plane should travel in order to compensate for the wind. Pause the video here, give this one a try. So since there's a strong wind from the south, we need to point a little bit to the south, right? If the wind's coming from the south, if we don't point towards the south, we're going to end up getting blown towards the north, right? So the long story short is we can draw Calgary right here. So we'll say that's Calgary right over there. There we go. Calgary's right there. The airplane is coming straight from the east. So it's a little bit east here. So this is our start over here. We want to get directly to Calgary. So the airplane is going to need to point this way, just like this, for the wind from the south to push it back up to Calgary so that our final velocity is actually a true straight line. So this one's a little weird. Since we're pointing slightly to the south, we'll say that that is going to be our 700 kilometers per hour. That's not the true speed of the airplane. That's just what the airplane's pushing through the air at 700 kilometers an hour. The wind is 90 kilometers per hour. So that's this side over here. This up and down is 90 kilometers per hour. So we need to find what this one is here. I'll just call it X rather than use a question mark. So we'll need that X. Oh, wait a minute. We don't need that X. It just says find the direction the plane should travel. Oh, that's funny. We don't actually need that at all. We just need this angle right here. That's funny. I should have read the question a little more thoroughly before I started there. I got carried away. So let's find that direction. Either way we do it, that actually makes this question a little easier. Either way we do it, we just have to use a little bit of right triangle trig. Notice that this 90 kilometers per hour over here, that's our opposite side from our angle. And our 700 kilometers per hour, it's not our adjacent side. Be very careful. Notice our right angle would be up here by Calgary. This is actually our hypotenuse right here. So we have our opposite and we have our hypotenuse. From SOHCAHTOA, that means we have to use sine. So we'll say sine of our angle is equal to our opposite, which is 90, over our hypotenuse, which is 700. To find that angle, we just have to use inverse sine. So inverse sine of 90 divided by 700. This gives us theta equals to 2 sigdigs, 7.4 degrees. Now let's be careful. We also need like the whole south and east and west and all that thing. So notice we are traveling west and south. So by this, it would be south of west. So 7.4 degrees south of west. And again, I got that south of west just by looking at the picture I drew here. In order to get to this end location, it's like in terms of X's and Y's, we went west first and then south in order to get that. That can be a little sneaky and tricky sometimes, but it is what it is. With a little bit of practice, it should come around. Remember the final review booklet that you'll be working on, the answers are provided in there, as well as the answer keys posted on Google Classroom. So what that leaves us with is that final review book that I just mentioned. So make sure you are trying some of those questions in there. It is really, really crucial that you get that kind of practice in. If you need any help, please make sure you are reaching out. Best of luck.